thanks everyone for being here today. My ambition has been to bring together professionals and novices, researchers and enthusiasts or students around the astronomy of tomorrow, viewed through the lens of citizen science, and which makes observing the night sky a leisure activity based on fun, sharing, exchange, and communication. I'm all the more proud to have initiated Stellar Collective without being a professional, a researcher, or even a knowledgeable amateur. Just someone curious about the cosmos, happy to see that astronomy and science are now accessible to everyone thanks to innovative observation products like digital telescopes and projects using technologies within everyone's reach, and initiatives aim at the widest audience, meaning people like me, but also and obviously like you. This afternoon, we will be hearing about exciting projects led by people who make sharing and collaboration the key of their initiatives. I thank them in advance and salute them. I'd also like to take this opportunity to thank our sponsors, Brilliant, Story Hospitality, Unistellar, and Boise State University. I wish you a wonderful afternoon that will conclude with a practical sky observation sessions and also with a few drinks together. I close by thanking Ariana Giappalucci, our project manager, and now I will hand things over to her. Thank you. Enjoy.
All right. Hello, everyone. I hope it's on. Is it on? Perfect. Hi, my name is Ariana Giappalucci. I am a senior here at Boise State University studying astrophysics, and I'm also the project manager for this Stellar Collective conference. It's been such an honor to help bring this project to life. This conference is deeply important to me because I believe there's often a certain perception around science, especially in areas like physics and astronomy, where many people decide that they're not smart enough to participate before they even give themselves a chance. And that's something that I've dealt with personally. My love for astronomy began in 5th grade when I saw a video about the solar system. That spark stayed with me through middle and high school, but when it came to apply for college, I chose psychology. I don't know why, probably fear. I knew astrophysics would be challenging, and I doubted whether or not I was good enough. Even today, I sometimes wrestle with that doubt. But my college journey has taught me that you'll never feel fulfilled unless you chase what you're truly passionate about. When I was majoring in psychology and later elementary education, something always felt missing. Now, pursuing astrophysics, even though it's hard and even though sometimes it drives me genuinely insane, I know that I'm exactly where I'm meant to be and I wouldn't change it for anything. Astronomy matters because it connects us to the generations who looked at these same stars before us and to the mysteries of the universe that humans have asked since the beginning of time. The universe is our home, and by understanding it, we understand more about ourselves and the world. That's where citizen science comes in. It gives everyone a voice. It makes it possible for people in the community to help discover exoplanets, track comets, study asteroids, and so much more. When we include everyone, we make discoveries and we move further faster. My hope is that when you leave this conference, you feel inspired and confident that you can do science, that no matter who you are or what experience you bring, there's a place for you in discovery, that you have the right to wonder, to question, and to explore the universe. With that, I'd like to welcome your first keynote speaker, Dr.Franck Marchis. Thank you.
Thank you. Hello, everybody. Thank you very much. So, first keynote speech of the Stellar Collective. I'm sure that in the future we're gonna have videos or pictures of this, and we're gonna talk about the first time we organize this conference. I'm very happy to be here to talk to you about something new, something I never talk about, in fact. So let's see if this works. So, first of all, I'm a researcher. I work at the SETI Institute, the Search for Extraterrestrial Intelligence. You're gonna hear about us quite often today. Ah, now it's working. But I am also an entrepreneur. I've been part of the Unistellar company for 7 years as a chief science officer, and also created recently a company called SkyMapper. And this is the talk, the first time, as I mentioned, I'm going to talk about SkyMapper to the public. So let's see how it goes. I merged two talks with the idea of speaking very quickly. So fasten your seatbelt. It's going to be a lot of slides. No, 30 slides only. Okay, so I know we're here to talk about citizen science and science in astronomy in general. But I think it's always important as a human being, whatever you do in your life, whatever choice you make in your career, in the life you have, to always wonder why you're doing it. What is the true motivation for the work you're doing? I often wonder if I become an astronomer because I wanted to know whether or not we are alone, or if I decided to dedicate my time to citizen science, to sell telescopes. But in fact, it's none of these. One of the reasons I become interested in citizen science and bringing back astronomy to people is because I was lucky enough to be born in the 70s and to be able to see the Milky Way from the city, from the countryside where I grew up. And I do remember seeing the sky, seeing the Milky Way, talking about it with my family, my friends, and dreaming about the worlds that could be over there, watching Carl Sagan on TV, etc. And this truly inspired me to become who I am now as a human being and as an astronomer. And I think it's important we keep this connection with the cosmos. And fortunately, we are using more and more those lights, those LED, that everybody seems to enjoy having blue in their face. And those are making us blind. We are losing the connection. You look at the sky now in cities like San Francisco, where I live, or here in Boise, you may see 10, 15 stars. And that's all. How can you dream by seeing only 2 or 10 tiny dots in the sky? How can you dream about going there, traveling there, building an infrastructure, an hotel, going on the moon? You will not be able to dream about that by simply seeing only 2 tiny dots in the sky. So we created the Unistellar telescopes. I participated to citizen science event and citizen science astronomy science because I believe that we need to reconnect the people in our generation and the future to the cosmos. And that's the reason we created, as I mentioned, Unistellar. That was really the key motivation for me. That was to build an instrument that anybody can use and will bring back the wonder of observing the sky together, listening to music, drinking some tea or wine or whatever you want, and chatting with your friends and having this crazy conversation about the cosmos. That was the reason we have created this instrument, and I think that's also the reason for which it has been so successful. We have now more than 17,000 of them all around the world. You will see tonight how they work and what you can see with them, hopefully, if it clears out. And yeah, it's kind of magical. So this is great. We provide an instrument to connect the people to the cosmos, but we also wanted the people to feel that they do something more than being part of the adventure of space exploration, or making our species a true spacefaring species. And that's the reason we have those citizen science programs. So I'm going to describe a few of the results we obtained with the citizen science program at Unistellar, and then I'm going to switch to SkyMapper, because I think it's important you understand the transition between the two projects. So as I mentioned, we created an instrument that provides pretty pictures, and the strategy is that we get nice pictures, but then you have the telescope, you say, hey, I can do something better with this telescope. Maybe I can do science. And that's possible with any telescope. I'm not saying that you have to have this telescope. It can be with any other telescopes. You can do observations of comets when they come close to us, asteroids, etc. So we partner with the SETI Institute, the Search for Extraterrestrial Intelligence in Mountain View, to develop the citizen science program. And there is multiple people here who have been working with me on this project. We're going to see Lauren soon. We're going to meet Ariel as well. Lauren is our exoplanet lead, and Ariel is our comet lead. So if you want to hear about comet and exoplanet, you should talk to them instead of talking to me, of course. This tiny dot here on this map is basically some observation, citizen science observation that has been taken in the year 2024. The different color is different type of science. Okay, some people observe asteroids, some people observe comets, transient, cosmic cataclysm, nova, etc. We have 11,000 observations taken in 2024. So I can say that we are the largest network of citizen astronomers in the world with this project. So I show you tiny dot moving here, but behind it, there is a lot of computer analysis, a lot of algorithm, a lot of complication to put this together, to extract the information, to extract what we call astrometry, photometry, all of this. And I want to give you a lecture about that. So I'm going to go straight to the result, so you see what we get. But you should imagine that behind every slide I'm showing to you here, there is the work of 1 month, 2 months, sometimes 6 months of one of the person in our team, including astronomers, engineers at SETI, at Unistellar, but also other institutions around the world which has been working with us. So with a small telescope, such a this one and others, you can see asteroids. Asteroids, as you probably know, orbit between Mars and Jupiter for most of them, but we have the near-Earth asteroid that cross basically the orbit of our planet. Those near-Earth asteroids, when they come close to us, there's just tiny dot moving in the sky. So that's what you see with our telescope, for instance. But if you analyze the tiny dot and the location, and as well as its brightness over time, you can have a lot of information. You can have the orbit of the asteroid. You will be able to predict where it will be located the next time it passes nearby our planet. You will be able to also get an idea of the shape by looking at the variation of light as the asteroid is spinning on itself, and also the pole orientation, etc., etc. So this is a work we have done in 2020. That was one of the first asteroids we observed with our network, and we have the shape estimate on 1999 AP10, and this is a work that was done with Joey, if I remember, who is also here. And we have 26 astronomers who observed this from everywhere in the world. So it was kind of a coordination campaign where we asked people, hey, you have an asteroid passing by, we don't know the shape, we have a poor idea of the location, and these 26 people took the telescope out and observed for 20 minutes, 1 hour this asteroid. We combine all this observation and we get this shape. So this is the power of citizen science. You cannot do that with professional telescopes, because you will always have, if you observe in Chile, which is one of the best sites in astronomy, I live there and I tell you there is night where there is weeks where you can see the star because it's cloudy. If it is cloudy when 1999 AP10 is passing nearby you, you don't have observations. We have a network which is distributed spatially, so we can see any asteroid at any time if we have someone who will basically take his telescope out to observe it. So that's really the power of citizen science, is to basically overcome, we overcome the small size of the telescope by having multiple telescopes and being able to do this large number of observations. This is one of the famous results we collected in 2022. You probably remember when NASA sent a spacecraft to impact Dimorphos, the moon of Didymos. And this impact happened when the asteroid was visible in the southern part of Africa. We have telescopes there. That's also the strength of our network. We have telescopes everywhere, and one of the places is Réunion Island, which is 1,000 kilometers east of Madagascar. It's a small island, and we have like 5 telescopes over there. And Bruno Payet took his telescope out. He observed the asteroid, and you can see the asteroid, and you can see the moment there is the impact with the DART mission, you see the puff, the explosion, basically. So from this image, this animation, Ariel Gekowski, who is here, spent months and months doing analysis, and she basically confirmed that one, the impact happened, that was obvious, but also that this impact basically modify the orbit of the asteroid. So this is the first time humanity shown that we can deflect an asteroid which is 100 meters size in diameter. And this is important because we know that this kind of impact could happen in the future. The probability of an 100-meter diameter asteroid impacting our planet is 1 every 10,000 years. So it's possible. It could happen tomorrow. So in this case, we know that we have now the technology to divert this type of asteroid. And this result, this confirmation, was done in our case from a group of 35 citizen astronomers. Something more fun and more complex is to observe what we call occultations. So in this case, we don't observe the asteroid. We simply wait for the asteroid to pass between us and the star. And then when this happens, the star will simply disappear. And if you have multiple people along the path of the shadow of the asteroid, when each of these people record the occultation, the disappearance of the star, they will be able to have the exact position of the asteroid, extremely useful if you want to know if it could impact us in the future, and also the shape and the size of the asteroid. So we have done that multiple times. We have thousands of those occultations. But this is the one that I really like because we targeted an asteroid called Eurybates, which is a Trojan asteroid. It's an asteroid orbiting very far away from us. It's basically in the Lagrange point, the equilibrium point of the Jupiter Sun system. And it's going to be visited by a spacecraft. NASA launched the Lucy mission that will arrive, I think, in 2032, something like this, to Eurybates. But NASA doesn't know anything about this asteroid. We just know its orbit, and we have a rough idea of the size, and that's all. So we alerted our network and others to observe this occultation. And the occultation was basically the blue band you see here is the probability of success of an occultation, of this occultation. So we have 300 people in Europe that basically register on the system to be able to observe this occultation. And we have 18 of them that saw this occultation. So when you look at an occultation, this is what you see. Look at the star with the blue circle here. You see it disappear for a moment? And this disappearance is basically because an asteroid passed between us and the star. And this was visible if you were on the blue area here. So from this multiple occultation band, chords, we call that, so each of them is an observer. We derive basically the shape, roughly the shape of the asteroid. And if you look at this one here, this chord, you see that the observer saw it disappear, reappear, and disappear again. And that's what we call a grazing event. And they are very useful because they give us some information about the age of the asteroid. And now we know that Eurybates has a crater, a big crater in this location. There is multiple observations that confirm that additional occultation, but this is the first detection. And this was discovered by Jean-Michel Ladrouz, who is a French person living in La Roche-Saint-Sidrine. He texted me when he saw this. He was very surprised. He sent us the data. We put the data together, and now the NASA Lucy team is using this data to confirm and to confirm the existence of this crater. So this person, in his backyard, with a telescope, discovered that a tiny 100-kilometer asteroid floating nearby Jupiter has a crater. I think it's always amazing what we can do with the technology we have now and the knowledge we have in our solar system. Okay, Comet, I need to talk about Comet because Ariel will be very upset if I don't. And you know that comets are super cool because we never know what's going to happen. The stories of, for instance, 2025, I got an email from the Unistellar team asking me, hey, will there be any comet in 2025? And I asked Ariel, and we look, and there was no comet predicted, or except one in October. But in fact, now we know that 2025, we will have a lot of comets. We have 6 of them, if I remember, coming at the end of this year. This is one comet, I forgot, this is Leonard, if I remember. But what is interesting with comet is that sometimes we discover them very late, like them very close to us. And sometimes when we discover them, we have a rough idea of the size of the nucleus or the type of activity, so we make predictions, and they surprise us. Sometimes they fizzle and they disappear very quickly, and sometimes they become extremely bright, and we see something wonderful in the sky. So that's why I like comets, because they always kind of they play the game with us. The theorists have all these great ideas, and it's always something completely different which happened. So this is one of them. I think this one was in 2024. That's 12P Ponsbrook. It's been observed by a lot of our citizen astronomers in our network. That's the tiny dot, yellow dot you can see here. On the right, on the x-axis is the time, and on the y-axis is the brightness. So to give you an idea. And you can see that theoretically, this comet should follow this line. And as you can see, it does not. This is a comet which has been has the most erratic behavior in 2024. And we don't really know why. We suspect it's due to a weird composition and the fact that it's heterogeneous. It's not made of the same mixture of ice and rocks in the interior. And that's why it has this kind of outburst, suddenly has jets, and then suddenly cool down again, and jets again, etc. So this is something we can do with citizen astronomers, and only them, because most of the time those large telescopes are not accessible to do this kind of survey. So having again a constellation or small telescope, multiple eyes looking at the sky, allow us to do this kind of studies and understand better the erratic behavior of comets. Okay, so now I'm going to talk about the new thing. The new thing is SkyMapper. SkyMapper is basically an evolution of the classical citizen astronomy that I showed you before. What we're trying to do here is to scale the potential of these individual telescopes and instruments to build a decentralized network so people, professional astronomers, amateur astronomers, can contribute and also access to the data. Who here ever heard about decentralized science? Wow. Okay. So the decentralized science is a movement which the idea of the decentralized science is basically that science should not be limited to universities. Scientific studies should be accessible everywhere. So anybody could be a scientist. But for this, you need to make sure that the data that come out of those scientists are validated somehow, that we know they have not been artificially modified. You know that nobody cheated, for instance. Because science relies a lot on the data which has been collected. So there is this relation of trust between scientists. So if we allow everybody in the world to be scientists, we need to find a way to provide the data in open access, transparent, but also making sure that these data have not been modified. So that's the technology we're using here, is basically blockchain technology as a validator for the data. The reason decentralized science has been a movement which is growing over time is because it brings a lot more people in the scientific discussion. And bringing more people in the scientific discussion, especially people from other countries that the Western world, allow this country to take ownership of discoveries and to be part of the technological development of our civilization. So there is a lot of different topic in decentralized science, but in our case, what is very important for us is that the data coming from telescope should be somehow validating and immutable. We need to make sure that we can also trace who took this data and where they went, when they were taken. The second part of the SkyMapper is what we call the decentralized physical infrastructure. And this is very new. This started like typically a year ago. And the goal of that is to basically make sure that small hardware that you have in your house or you wear on yourself, like watch, phone, sensor, like weather sensors in your house, they're basically connected. So what I mean by that is that if you had a watch which is part of the decentralized physical infrastructure, the data collected by this watch, which are you data, is you walking, is you health, you heartbeat, right? When they go to a database, first of all, you need to allow it. Secondly, the data are labeled, such as we always know where they're coming from. It seems to be a lot of people don't care about that. A lot of us wear these watches or their phone, walking around and providing data to corporations or to groups of people, and we basically don't care about it. We don't really know what they do with it. The decentralized physical infrastructure, the idea is that you always know what happened to your data and what this data is going to be used for. And if millions of dollars or a major discovery is made because of your data, you part of this discovery. You have the ownership of this discovery. I like the idea, and that's the reason SkyMapper is part of this kind of infrastructure. And then the last part is networking science. So in this case, basically, we want to create a network of telescopes, in our case, and sensors, sky sensor, that can work together. And we share the data, they validate each other. If a telescope detects something, a new comet, a telescope nearby which is capable of observing will point toward this area of the sky and confirm the existence of this comet. That's what we call networking science. So SkyMapper was born in 2025, so it's very new, in March. And we're experimenting right now. We're building this network. So we have connected already a dozen of telescopes, unistellar telescope to start with, but the goal is to have thousands of them in the future. So allow people who have telescopes to connect to our platform and to participate to this network by providing data, but also by participating to the analysis, the processing, etc. So what I meant when I say decentralized, which is kind of a word I'm going to say a lot, is basically distributed. So when data come from the Unistellar Citizen Science Program, the classical one, they send to our server at the SETI Institute, and we do the data analysis, the processing, and then we send the data back, the report back to the user with an explanation, a report, etc. In our new system, basically, each computer that we call Sky Bridges here is a tiny computer that you connect the telescope on, will be doing this. So we have a distributed network. So if this telescope observes a comet, a field of view, and search for a comet, another computer will be able to do the analysis with the help of a validator somewhere else. And when a result is being captured and need to be stored, it will be stored the same way on a distributed platform. The advantage of that is that it makes the system much more robust. It will never crash. Because if one computer dies, it's one tiny node in a large network. If our Google server dies, we basically lost weeks of data analysis that we have to restart sometimes. So this is one of the reasons we are focusing on this kind of distributed network. So I'm not sure I want to bore you to death with all the blockchain. How much time do I have? 5 minutes, so I'm not. But if you have questions, I can explain to you how we use that exactly. Okay, so we have done, it's 5 minutes with questions, or without question? Oh, wow. Okay. So we have a system that is working now, and in October 6 or 7, you're going to be able to connect to it, and you're going to be able to take control of a telescope. And if I have time later, I may show it to you live, because I have multiple telescopes connected on our platform now, so I can do a demonstration. So but basically, you choose the telescope you want. In this case, for this screenshot, I took a telescope in Vienna, in Austria, and you can control it, like if you are nearby. And you basically can acquire observations, request type an observation, scientific or just pretty picture like we are doing now. And in the future, we're gonna work on an API. So if you want to observe a part of the sky every 15 minutes, for instance, you will be able to request that. And any telescope which has access to this part of the sky, to this asteroid, will be able to record an observation. And you receive this observation on your computer. So that's the idea of making astronomy decentralized and more worldwide, basically. There will be always a telescope available on our platform. That's the goal. So we have done some first results. Since you have seen some already with the citizen science of Unistellar, you can recognize some of those. This is a comet that was observed from California. This is the interstellar comet. You know that we have a comet coming from another part of another planetary system, which is now visiting us, right? And there is a lot of craziness being mentioned by the media now, but frankly, it's just a comet. It's slightly different than the comet we have probably on our solar system because it has a different composition. But this is the kind of things we can do with our network. We can observe this comet continuously, measure, for instance, the ratio of dust versus gas, the color over time, etc. And we have a much higher density of observation that we will have if you have any classical network, because we will have in the future thousands of telescopes connected. This is another comet, 2024 E1, and I'm going to skip that, but we have been detecting it. We can measure the brightness, etc. And this is a diagram that was the first observation. We took that in September 1st, so it's very new. But what you can see, this tiny dot here, is basically the brightness. So Ariel sent us from the brightness of this dot an estimate of the brightness of the comet if it behaves normally in the future. And it may reach magnitude 6.5 in February 2026. But that's not enough. For points like this, it doesn't help you. So in the future, we will be able to observe almost continuously this comet, and so have a very good estimate of the brightness evolution and make a better prediction of the future brightness of the comet, for instance. So this is the reason we are working on this project. SkyMapper is really to densify the number of observations in science. We don't do only comet, we do supernova, variable star. I'm going to skip that. But we also do more than connecting telescopes. We are working now on different type of instrument. We have an enclosure that will be available in the future in 2026. We're working on the all sky camera. So an instrument that can observe the entire sky above your head. And the mechanism is the same. You buy the instrument, you set it up in your house, and you say, yes, I want to send the data to the SkyMapper platform. So we receive regularly observation of the weather above your house here in Boise, Idaho, but also we'll be able to see there is things flying in the sky, airplanes, drones, or see satellite re-entries. A lot of satellites are now being sent to burn into our atmosphere. We need to be able to measure that. So we'll be able to, with this instrument, to do this, see meteors, etc., etc. We're working on different type of agent, AI agent. Since we have a large amount of data, and these data are all accessible, available, we can start building smart agents that will analyze for us the data. So the vision here, we want anybody that has an interest capable of going to our platform and say, send me all the observation of the comet 3I Atlas and extract for me the brightness or calculate the position or the orbit of this comet. And the system will basically be smart enough to do this analysis, extract the right observation, etc. That's, I think, the science of the future. And that's where we are going. I'm going to skip this because I have not time, but we also do drones and meteor detection with this instrument. This is a simulation based on real observation. You have a tiny green square here, which is basically the detection with an AI-based algorithm of a drone flying above the station. So if you have that instrument, you'll be able to be warned if something happens. I don't know, you don't like your neighbor sending drones above your backyard. Here we are. We have a system to do it. You want to be able to see meteors. So if something, for instance, fly above Boise, Idaho and crash not far away, you will be the first one to get the pieces of the meteor because of this instrument. So there is a lot of potential here with this instrument. And since more and more people are interested in astronomy and what's happening above our head, we believe that this is a solution and the solution for this kind of problems. Okay, so where are we going with this project? So we are, in 2026, we're going to finalize basically what we call the tokenization. If you have questions about that, I can answer to you, but it's basically a metric. So you earn tokens, and you can basically use them to do analysis, etc., or exchange with other people. We're going to put larger telescopes on our platform. We're already discussing with professional telescopes in Canary Island, in France, and in Hawaii to have the 0.5, 1, 2 meter class telescope on our platform. So that means you will be able to do control of this using the SkyMapper. And the goal is to do astronomy of the future, basically. 100,000 observations taken in a year, at least. So we map the entire sky. We map asteroids. We react quickly when the Vera Rubin telescope will discover a nova or anything weird and bright in the sky, like the laser pulse of an extraterrestrial civilization. You're going to talk about that, right? We will do the follow-up. And also, so it's not only about computers and instrument. It's also about community. It's also about growing a community, creating a community of people that work together on this project. We will not reach 1,000 telescopes if we don't build a community of people who really believe in our project. And we also want to diversify. We are sending telescope at the moment in Argentina, in Chile, soon in Egypt, and we are looking at countries in Asia as well. And to conclude, so in 6 months we have created this first Web3 decentralized astronomy network. We know it works. Now we are going to accelerate the development, get real scientific observations, and more platform and more instruments connected to it. We're gonna need help. I'm gonna be very direct with you. We need to grow a team of engineers and astronomers to reach this vision, but I think it's possible. And we also would like to have more collaboration with university, amateur and professional astronomers as well. And I think I'm gonna end here. Thank you.
It does work. Okay. So after every talk, we'll have about 10 to 15 minutes for questions. So if you have any questions, please raise your hands and we'll bring mics around. This one should be on. It's turning on right now.
My question is, how do you ensure all the telescopes have the same time? And what is the error in the time between telescopes?
So the SkyBridge, which is the tiny computer I mentioned to you, will have a system to calibrate the time. In fact, it has already a system to calibrate the time. Our goal is to reach 1 millisecond accuracy on the time, so we can do very fast occultations, for instance. And the accuracy on the ground will be typically 1 or 2 meters.
Hello there. So basically, I have the question is on when you collect the data based on all of the devices, does the device do auto labeling and or it just sends the data back to the server that you have and the server does the analysis?
That's a very good question. So we partner with a company called Akave. They do decentralized data storage. So basically, when the data can go out of the telescopes and been validated by our SkyBridge, they will send them for storage on this platform, which is also on-chain. So we know where the data goes and so on, and make sure it's not been modified. And then when the SkyBridge will do analysis, because this is not yet implemented, just so you know, they will basically access directly to the Akave server to retrieve the data. So even if the data will be spread on the Akave network, we'll be able to retrieve them.
My question is about the all-sky camera. The data that's downloaded, is it possible for that to be integrated with sky cameras of other manufacturer?
That's the goal. So one of the problems we have with the SkySphere is that we started recently this project, to be honest, and there is a lot of do-yourself use sky camera. So we are looking around who have manufactured all sky camera, and in this case, if they want to be part of our platform, the user will just have to purchase the SkyBridge, and we will create the API to connect to this camera. That's
Thank
a project, yeah.
Any other questions? Okay, awesome. Well, oh, lied.
Do we have time for that or no?
You have 5 minutes.
Okay, so let me try something which generally fail when I try. 7 minutes, wow, she's tough today with me. Yeah, of course it doesn't work. Okay, let me just log out. We're gonna do like what we always do. Okay, so that's the sky viewer. And someone is using the telescope, Bruno. So this is basically the telescope which are connected right now on our platform. And this one is in California, this one is in Japan, and this one is in Vienna, but someone is using it, from Bruno. So I cannot demo it because he's using it. I could text him and tell him to get out, to leave, but let's be nice. If you want to see it in action, when we have a break, I can show you. Okay? Sorry for that.
Okay, well, if we could give one more round of applause to our speaker.